Yes, Sai, you have any questions on the material so far?
We are live, sir.
Good morning, Himanshu.
Good morning, sir.
Yeah. So, yeah, I mean, if any of you can, if you have any questions, please to go and ask them. Can you hear me? Is there a lag or something? You can go ahead and ask your questions if you have any.
Sir, here how the analysis go through the pendant drop? If the drop is if the
I couldn't hear you. Can you just repeat that again?
due to network issue, I am.
Or maybe you can just type your question in the chat.
Yes, sir.
You could also chat the question if you wanted to. I think there's also a YouTube live stream. You could also chat it, type your question over there.
Pendant drop.
Do you want me to go through the analysis of the pendant drop?
Yes, sir. Yes.
Which particular? Okay. Can you
Means
be more specific?
when how for how much of
I can't hear you. Sorry. I simply can't hear you. Or you maybe just type the extension as well. Can you be, because in the course as such, we didn't really explicitly discuss any analysis for a pendant drop. So you can basically type your question so that if you want me to go through some analysis or give you some brief idea of how to do analysis for a pendant drop, I'd be happy to do that. Are you able to hear me? Can you say yes or no? Are you able to hear me well?
yes, sir. I am able to hear,
Okay.
but my network is that's why.
Okay, so if you're able to hear me, let me just repeat what you said, and you can confirm whether the question, did I understand the question right? Do you want me to briefly explain the analysis of a pendant drop?
Yes, sir. Yes, sir.
And is this in the context of, let's say, measurement of surface tension?
Yes, sir.
Is that the idea?
Yes, sir. That is my idea. How the surface tension works on the pendant drop.
Okay, okay. So in the okay, so first step is basically to look at the Young Laplace equation. What does the Young Laplace equation represent? It basically it's an equation that emerges out of basically looking at the balance of surface tension and gravitational forces. Right now. Now, the gravitational forces basically depend on the weight of the droplet, and surface tension forces depends on the local curvature. Okay, so what we essentially are doing is basically we're solving the Young-Laplace equation. Um, uh, uh, we can actually, and we also have to specify a volume constraint. The idea is very simple. I mean, it's actually not that simple, but it can be done. The idea is the following: you can basically let me just see if I can. This wasn't really part of the course, so I didn't really. Um, Let me just add one more section and maybe share my screen. Um, okay, so can you see the screen?
Yes, sir. Yes, sir.
Okay, so the idea is that you you this is basically the needle. Okay, and
Yes,
from
sir.
this needle you create a pendant droplet. Okay,
Yes.
okay, and then you also say that the volume of the pendant droplet is V. Okay,
That
now
voice
once
is
you
not
specified the volume of the pendant, sorry,
voice is not clearly audible to me.
uh, Himanshu, is it clear from my voice? I'm just trying to understand whether the issue is with the sound on
Now
your side
it
or
is
this side.
now it is clear, sir. Okay.
Okay. So the idea is that you create a pendant droplet from a needle and you dispense a certain known volume. Okay. Once you have
Okay.
specified a known volume and you create a pendant droplet, then basically you determine the shape of this droplet. In particular, by and large, you're looking for the curvature over here.
Okay.
Okay, once you've determined the curvature of this droplet, because once you calculated the shape of the pendant droplet by solving the Young-Laplace equation, the curvature of this location the curvature will tell you the balance of forces. And
Okay.
this curvature that you get here, this will be a unique curvature for a given surface tension.
Okay, sir.
Okay. So when you are trying to use when you if you're using a contact angle meter, or let's say you want to build your own contact angle meter, what
Okay.
you're really looking for is to dispense a fixed amount of volume. So the volume is fixed, and you're trying to solve the Young-Laplace equation with the constraint that the volume is V.
Okay,
And
sir.
once you've done that, you basically get the curvature, and from the curvature you determine the surface tension.
Okay.
Okay. I mean, I'm saying this extremely briefly, but that's the basic idea.
Okay, sir. Here, how we know that the volume of the that means that means how we know the volume is this only? How we describe
Yeah. So that
initially?
for that typically yeah, you will have to prescribe a certain amount of volume. So it means that when you basically do the pendant drop method, you will have to use some kind of a contact angle meter for doing this. Okay.
Okay,
So,
okay, sir.
but we can go into more details. The idea is that the idea is basically simple. The pressure difference at the interface, that is basically the pressure inside minus pressure outside. We know it is just simply equal to surface tension times the mean curvature, 1 by R1 plus 1 by R2. Correct?
Yes,
Hmm?
sir. Okay. Yes, sir.
Now once you've created but the pressure on the inside, the pressure difference that you get, okay, this pressure
Okay.
is simply going to be the change in the pressure because of surface tension plus hydrostatic pressure. And the hydrostatic pressure will simply be, oh, I think I just stopped sharing my screen. The Okay, so the hydrostatic pressure is basically the depth.
Okay.
Once you know the depth, you basically know the hydrostatic pressure, and you have to determine that will give you the curvature. We are now here at the very base, at the very bottom. I'm showing the bottom because in the bottom, the two curvatures are the same. Basically, if you look at it from the bottom, this part will look like
Yes,
part of
sir.
a sphere. So your 1 by R1 and
Okay.
1 by R2 essentially become 2 by R. So your delta P that you have
Ah,
here
yes.
essentially becomes
Okay.
surface tension, let's say gamma times 2 by R.
Yes,
Not
sir.
this R. Um, 2 by R. So now the delta P itself is basically going to be from hydrostatic pressure. Okay, because you would know that this would be like rho GH, rho GZ. Okay,
Okay.
and for I'll give you a very simple idea where you would need this. For example, if you dispense a certain known volume. Now, if you basically take a very large volume, then essentially the droplet becomes so large that it will just drop. Okay. If you take a small volume and
Okay.
you're able to create a pendant droplet, now imagine what's going to happen if you use surfaces of different surface tension. If you use a very high surface tension, what's going to be the shape? Let's look at that. If you use a very, very high surface tension, then for the same volume, it is going to be, let's say this is the shape. But if you use a very low surface tension fluid, oh, sorry. If you use a very low surface tension fluid, then it's
Yes,
very
sir.
likely that it is going to be stretched.
Okay.
So the local curvature in both these cases, the local curvature, let's say over here, versus over here, is going to be very different.
Okay.
So this is also consistent here. The delta, here you're also going to bring in the hydrostatic pressure because essentially that's what is bringing it down, and the gravity is resulting in the hydrostatic pressure, and the low surface tension would mean that the droplet will basically become like this, whereas if it's a high surface tension liquid, then if you make it it will hold the droplet, it will be more spherical in shape, and that will lead to a larger value of R. Okay.
Okay, sir.
So that's the general idea of how the pendant drop method is used for measuring surface tension.
Okay.
Is this clear?
Okay. Yes, sir.
So what is normally done in a, I mean, you have to determine curvature. So to determine curvature, what you have to further do is you have to solve for the shape of the pendant droplet. Okay. So you solve for the shape of the droplet in the especially the lower part. Okay, and it's convenient to write this down in terms of arc length coordinates. Okay, where you write down equations for the shape of the droplet in terms of the local arc position. Let's say from measure from the bottom and the arc angle. Okay, measured from
Yes, sir.
some convenient point in the middle, and you would write down a series of differential equations for how the arc angle is changing as a function of arc length, how the x coordinate is changing the position, and how the z coordinate is changing. Meaning, you are basically trying to write down the equation for the surface, and while you solve for this equation for the surface. Once you solve for this, then you basically can get the only unknown will be r. Now the idea is that the the unknown R can be determined by fitting the unknown R is measured from the image that you take. Okay. Once you know the unknown R from the image, then you can determine surface tension. Or if you know the surface tension, then you can find out what is the value of the radius of curvature. Any other questions? Fine.
No, sir. Thank you, sir. Thank you, sir.
Okay. So Once you have a question.
Hello.
Hello. Yes.
Sir, am I audible? I'm audible,
Yes,
sir.
you are audible.
Sir,
Yes, you are.
I had one question regarding the time scales. So, sir, the length scales we can understand, like there are various length scales, but the time scales that we are talking about in the so I just wanted to ask, like, what do you mean by time scales, and like, is there an analogy with turbulence here, or we are talking about different, different thing?
Is there did I hear you? I just want to make sure I heard you. Is there an analogy with turbulence? Is that what you said?
In time scales, yes, sir.
Okay. Okay. So, is this a broad question, or is it specific to any particular
In
point in the course where I mentioned time scale? Let's say.
Sir, yes, actually, so we are discussing about length scales at various places. Of that one question we also had, that lambda by L. So that is there, but I mean, is there length scales varying is okay, but is there a variation of time? So are we talking in the two-phase flows, are we also talking about that variation of time scales? Does that also happen? Is there an analogy with turbulence where we have both time scale and length scales varying at different? So
Okay. Okay. So I'll give you. I'll first give. I think I get the impression that this is also a broader question, not just to any specific problem. It is not the it's not that there is an analogy with turbulence. There's no analogy as such with turbulence. The idea is that whenever you have problems where things are changing with time and things are changing in space, then you may be interested in first finding out. Let's look at this problem. What is the things changing in in space? Okay, let's look at that problem. Okay, and again, I'll illustrate this with a simple sketch. Okay, and this is of course a very rough problem, and I've chosen an ending problem, not necessarily relevant to this course. So, but the idea is to emphasize how these things emerge. Okay, how lens skills and time skill emerge. Let's look at basically a convection in a box. Okay, this is some box, and in fact, the advantage that I have is I don't even have to say that this is a rectangular box. This is a box that I've drawn in shape. And let's say it's hot at the bottom, so the temperature is Tc, and cold at the top, Th. Sorry, it's the other way around. Water hot at the bottom and cold at the top. So at the top it is Tc, and at the bottom it is pH. Is this clear so far?
yes, sir. Yes, sir.
So now you can actually ask what happens. You know, is there a length scale that naturally emerges? Now, what is likely to happen in this problem is that convection, because the fluid is hot, it will try to rise up, and you can expect some kind of an overall circulation that sets up this way. Fluid rises like this, and basically some kind of a circulation sets up. Now, a natural length scale emerges in the system. Okay, which depends on the height of this box. Okay, so therefore that is one of the natural length scales in the system. But there could be other length scales in the system. Okay, now other length scales, as in, let's say there is a very fine convection that is going on. The flow is very turbulent, as you use the word turbulence. So in that context, the flow is very turbulent. Then the physics of the problem will dictate other length scales. Now, how do you determine those other length scales? You have to look at what are the other competing forces in the system. Okay. So here you can say one of the natural length scales is the overall size of the box. Okay. But you can also ask what is the time scale in the system. Now, when somebody says what is the time scale, what do you mean by that? What we mean is, you can ask, is there a characteristic time that represents this phenomenon? Now, one of the characteristic time that represents this phenomena is, what is if a fluid parcel which starts off here, somewhere at the bottom here, how long does it take for it to go around and come back to, more or less. Okay, this is like an overturning time scale. You understand? This is like an overturning time scale. Now, but the when you look at a problem, when you look at non-dimensional numbers, a classic non-dimensional number that most students in fluid mechanics would be aware of is Reynolds number. But what is the Reynolds number? Now, Reynolds number, you can think of it as the ratio of two forces, right? It's the ratio of inertial force to viscous force. Yes or no?
Yes, sir. Yes, sir. Inertial to viscous.
Okay. But is there any other interpretation of Reynolds number?
Except the formula,
Other interpretations of Reynolds number, not in terms of ratio of forces. You can write down the formula if you want. If you write down the formula, what do you actually see? Let me just try and give me a second. Maybe I'll come up with a better way to share the screen. Give me a second.
actually, sir, the reason why I was asking this question was at the first place is that we talked about the relation between K and omega, and that seemed to have like an intrinsic connection between omega, which was in the formula like omega t plus iota k z. So it seemed like some implicit relation between the omega, which was a coefficient of t, and the k, which was coefficient of z. That is why.
Okay, so okay, so I want to just broadly touch upon this point that you said. Let me just find. I have opened it on my iPad so that it makes it little easier for me to type this point more clearly. Can you see my screen?
No, sir, we cannot see the screen, sir.
Oh, I think it's just coming up. Give me a second. Do you see my screen now?
Yes, sir. Now it's visible.
Okay, so this should be a little easier. Hopefully, it will work. Let me just do this better. Okay. I was talking about Reynolds number, right? So let's look at that Reynolds number. So Reynolds number is basically you would write it as rho u some d by mu. This will be your Reynolds number. Okay. Now this is you will associate it as a ratio of inertia force to viscous force, and if you basically choose a relevant length scale and a time scale, then and you non-dimensionalize the Stokes equations, a Reynolds number emerges. Agree? So for this, you say that the dominant velocity is basically an inertial velocity. So u, the pressure would be inertial. So for u characteristic, you say is u. P characteristic is something like rho u square, and the characteristic time will be something like d by u. If you do this, then the non-dimensional term that enters the equation would be something like the non-dimensional equation would be del u star by del t star would be minus gradient of pressure plus 1 by Reynolds del square of U star. Your del is basically the a dimensional del operator. Okay, dimensionless del operator. Okay, so far it's okay, and I'm sure you know this. Now you can interpret Reynolds number not just as ratio of forces, you can also interpret ratio of length scales. How would we do this? You say it is D divided by, okay, um, mu by rho u. Okay, and so here, what are we trying to do is the following. So think about this is a problem that I'll explain a different problem. It's like you have a flow past a flat plate, okay, and you have a boundary layer. In this case, typically it's common to write Reynolds number in terms of a local Reynolds number. Let's say um, the Reynolds number at some position x. You will say Reynolds number based on that position is rho u x by mu. Okay. Now you can come up with a characteristic uh, length scale. Okay, the length scale is basically the length along which you are measuring the plate. So one of the characteristic length scale is x itself, or the length of the plate. But another characteristic length scale is basically some kind of a there is something that's happening perpendicular to the bound to this plate. What is happening perpendicular to this plate is there is diffusion of momentum. Correct? Yes or
Yes,
no?
sir. Yes. Yes, sir. It
Okay,
is.
so now the you can ask what is the diffusion of momentum. So let's say there is at any location, let's say I take it over here itself, at this location, delta would go over like what? It typically goes like root mu t, or this is basically the diffusion length. Mu we know is mu by rho times t, correct? And this
Yes, sir.
basically
It
is
is.
now okay. Now it is mu by rho. Now you say that this is if you have fluid traveling with a velocity u and it has to travel a distance of x, okay, then the typical time scale for the fluid would be t times time scale would be what will it be? X by u. Okay, so you substitute x by u. Okay. Hmm. So now you start uh, you start looking at these ratio. Okay. So now you think of uh, so if I look at the ratio of x by delta, that simply becomes x divided by square root of mu by rho u, okay, multiplied by x. That goes like x square, sorry, x power half divided by square root of mu by rho u. Got it? Now, if I define Reynolds number as, if I define Reynolds number, if Re is rho u x by mu, then which is same as x divided by mu by rho u, then this quantity x by delta is simply nothing but square root of x divided by mu by rho u. And this is nothing but square root of Reynolds number. So what does it actually tell you? Reynolds number is x by delta whole square. Got it?
Yes, sir. It is.
So this is another interpretation where Reynolds number is the ratio of length scales, or rather, it's the square root of the ratio of length scales. Okay, the whether it's square or not is a different matter, but the idea is that you can interpret Reynolds number in terms of ratio of length scales. In other words, Reynolds number essentially tells you by the time fluid starts from here and reaches this point, okay, the boundary layer has diffused a distance of delta from the bottom all the way here. Okay, the time it takes for the fluid to reach there is same as the length it takes to reach there would be same as the length it takes to go from the bottom to the top, the diffusion. You're equating a length scale because of advection, which is in this case happening because of inertia, a length scale because of advection, to a length scale emerging from diffusion. Is this clear? You can also do the same thing in terms of length ratio of time scales, Reynolds number. So if you do the ratio of time scales, you can ask what is the ratio of time scales? There is an advection time scale. Let's call it as advection or inertial time scale, which is simply nothing but x by u. Correct? And you can ask what is the time scale of diffusion. Time scale of diffusion would simply be delta square by nu. Okay, that is the diffusion time scale. Now, again, if you take the ratio of these two, you will again get the Reynolds number. So in many cases, if you think about non-dimensional numbers, they are ratio of, either they can be thought of a ratio of length scales or time scales. In this case, if you need to go one step further, you can interpret it as ratio of velocity scales. Okay. Now, in this particular problem, it may look like there are only two time scales. Okay, which is actually true. If we just do flow past, a flat plate, then the non-dimensionalization, if you do non-dimensionalization in this way, only one non-dimensional number emerges, which is the Reynolds number. But in a problem like multi-phase problem, like the kind that we have looked at, let me open one of these problems. Let's say,
Is it in the rupture time that we talk?
Yeah, if you look at rupture of thin films, okay, you can have several time scales. You can have an inertial time scale. You can have a viscous time scale. Here I've chosen L over U naught. Okay, if you have, you can ask what is the typical time scale for rupture. Okay, so what you do is you ask what is balancing, what is opposing rupture, what is causing rupture, van der Waals force. What is opposing this rupture? It is surface tension and viscous forces, because the very act of rupture will increase the surface area significantly, and you can expect that, and it also leads to large curvatures that are produced in the interface. Initially, it's a flat interface. Okay, so the van der Waals forces is therefore opposed by surface tension. Similarly, viscous forces also, because you're generating flow, viscous resistance is going to be generated, because that's how fluids oppose external forces. Okay, by flowing, they flow and generate viscous stresses, and that's how they oppose external forces. So viscous forces are also generated. Now you can ask, I can take the ratio of any of those two forces. I can take the ratio of, let's say, van der Waals forces and with viscous forces, and come up with a velocity scale or a time scale. I can do the ratio of van der Waals forces with surface tension forces and come up with an estimate for another time scale. So now what I'm trying to tell you is that there are several choices in a problem like this. Okay. Now what will be each of those choices lead to? What will each of those choices lead to is it will lead to a different set of non-dimensional numbers. Okay. You understand? But
Yes, sir. Yes, sir.
Now you can go back and ask something very basic. You can ask, first step you should ask in a problem is how many non-dimensional numbers are there in the problem. Once you ask how many non-dimensional numbers are there in the problem, if you get, let's say, 3 non-dimensional numbers as an example, okay, not specifically to this problem, in general, if I basically hypothetically, for a hypothetical problem, let's say there are 3 non-dimensional numbers, it says this is from Buckingham Pi theorem. It only means that there are only 3 unique non-dimensional numbers. If you choose a different set of non-dimensionalization, meaning if you choose a different set of length scale and time scale to non-dimensionalize your equations, you may get a different non-dimensional parameters. That doesn't mean straight away that the problem is incorrect or your analysis is incorrect. It's just that if you have to compare your results with somebody else, you have to be sure that your non-dimensional numbers and their non-dimensional numbers match. If you're using Weber number and somebody else is representing the results in terms of capillary number, then you have to make sure that you have to check whether if you want to compare with their published results, And if the results are all published results are in terms of capillary number, then you have to ask yourself, how do I convert my results into in terms of capillary number? So in a problem, there could be several time scales and several length scales, depending on what are the balance of forces that you're looking at. Here in this particular case, I've chosen one particular case where I have chosen a time scale and length scale based on the length of the plates, the horizontal extent of the plate, and a velocity u. And note that this velocity u at this point is unknown, because I will need an estimate for velocity. How do I get an estimate for velocity? I think I've discussed this later. Let me just locate the thing.
Yes, sir. You discussed, sir. Yes, I hear. Yes.
Maybe.
We made an estimate of velocity from that continuity equation that you are saying.
No, we will need an estimate. We will have made an estimate for velocity, typically from van der Waals forces. Just have to locate it. Give me a second. Yeah, so here you see there are the non-dimensional numbers that are present is of course the aspect ratio. It's a thin film, so epsilon is h naught by L. But then we have gravity parameter and capillary number, and another parameter which I called it as A bar, which is a non-dimensional Hanecker constant. This kind of an analysis you will find in the classical and absolutely excellent book of by Professor Gary Lee. And you can choose other combinations as well. This is not the only combination. You could choose Weber number and Reynolds number as well. But in these kinds of problems, the Reynolds number is not usually the parameter that the non-dimensional number chosen, because it tends to be you are anyway making an approximation that the Reynolds number is very small. This is clear. I'm trying to pull out some of the results where maybe I've chosen a different non-dimensional number. Okay, so let me just share another result, a result from one of my recent papers. I just need to figure out how to stop sharing this. Okay. I guess I'm not sharing anything now, but let me now share the screen. Okay, can you see a paper that's on the screen?
Yes, sir. It is visible, sir. It is visible.
Okay. So this is actually another thin film problem. Okay, this is with a student of mine, Vishnu, a few years ago, and we're looking at a thin film like this. And if you notice here that, let me just zoom into this portion. Okay, so we assume that epsilon, which is HYL, is a small aspect ratio, which would permit us to employ the lubrication approximation. The velocity components of fluid pressure are scaled as so and so. So you see here that I have chosen this non-dimensional velocity. This is a balance of viscous forces to van der Waals forces to viscous forces. Okay. So I'm asking, if I choose a ratio of van der Waals forces to viscous forces, what would be the, so I would look at the terms in the equations. If you look at the thin film analysis, you look at the thin film, the terms which govern the van der Waals forces. Okay, this will come in the normal stress balance. Okay, or you can add it as an extra disjoining pressure. Okay, as a body force term. Now you look at the disjoining pressure term and the viscous term. Okay, disjoining pressure would appear like del del phi by del x or del phi by del y, gradient of phi, where phi is the potential. And you basically balance this with the viscous term, then you a length scale emerges. That and a velocity scale emerges, sorry, not length scale, a velocity scale emerges. Now, here I further have written this is equation number 10, and note that what I've written subsequently. I said the scalings in 10 reflect a balance between viscous forces and the disjoining pressure gradient due to van der Waals forces. We also note that we note that our choices of scalings is different from that of another result of another published paper, where they have done a balance of viscous stresses to Marangoni stresses. Okay, and we argue that that particular scaling is not suitable for our problem. And then we also say that the natural choice for characteristic time scale, if you know the velocity scale, if you know the length scale, therefore you can come up with a natural choice for the time scale. Again, the time scale here is a reflection of balance of uh, the if you the term in the Navier-Stokes equation will be del u by del t. That will be the time derivative, the local acceleration term, del u by del t. You balance it with the van der Waals term. Okay. So when you do the balance it with the van der Waals term, you already have estimated a scale for u. Therefore, you can estimate a scale for t. Is it clear?
Yes, sir. It is clear, sir.
But note that this need not be the only source. Okay.
So this so the title of the paper is could I ask
Oh, you want to see what's the title of this particular paper?
yes, sir, this paper, sir.
Yeah, let me just share that again. Okay, can you see that?
Yes, sir. Now it is visible.
Yeah. I could look at let's say I'm just trying to see if I can open another paper where the time scale is very different. Um, this is okay. So I'll show you another paper where I think the again it's the same time scale. Yeah, so not that different. Um,
Sir, indeed, that when you highlighted that in course, like that rupture time we could get from balancing the inertia and surface tension. So that would also come from the same analysis if we do, and we put the inertia and surface tension forces instead of the forces that van der Waals forces that you have done here. So we'll get that whole root of rho r not q by gamma from there, from balancing the forces.
yeah, you will get the same thing. you can choose other choices, but you have to be sure about what are the what you have to know what are the relevant parameters in which you're operating. So you may get a different set of non-dimensional numbers, but interesting action will happen only when you are in the sometimes in the right non-dimensional range. Okay. So you have to have an estimate of what these non-dimensional numbers are, what's the range, what's the appropriate range for these numbers. So generally a good idea would be to have an estimate of various dimensional values for a realistic problem. And see how these numbers, what are the estimates for these numbers. So any other questions, Himanshu?
No, sir. I mean, it is clear and it is very interesting actually. I mean, I myself have been looking upon these scales in my, in my work. So I wanted to quantify time scales, and that is what I was thinking. Because many papers that I see are also talking about time scales, but since we did not clearly discuss that in the course, when this point came, like T rupture, so that time I thought like maybe there is something related, so I could extract that for my work also.
See, okay. The idea is, again, when we say characteristic time scale, the general idea is that if you've got the right balance of forces, meaning there is a particular driving force and there is a particular resistance force, retarding force. Okay. If you've got the right time scale, if you've got the right estimate for rupture, then what you will find is that when the phenomena occurs and the rupture occurs, then it will occur within in the same order of magnitude. It will occur in the same order of magnitude as your characteristic time scale. You understand?
Yes, sir. I get it, sir. I get it. Yeah.
But you choose a balance of forces and come up with a time scale, and that is not the dominant balance in the problem. And you come up with the time scale, you non-dimensionalize it, and go ahead and do the analysis. What you'll find is that the rupture that happens will be very far off from your characteristic time scale. So it could be you may have significantly overestimated the character, meaning what you think is that is not the characteristic time scale. That's what it essentially is telling you. You estimate the characteristic time scale to be some T reference, but then rupture happens, let's say 1,000 times or 1,000,000 times more than the faster than the T reference. Then it means that you are completely off with respect to your estimates of the forces which are causing rupture, because your T reference has been obtained with some balance of forces. Correct? Now, it is the answer that you're getting is telling you that that is not what is causing the rupture. The driving force, the retarding force that you have chosen is not the one that is causing the rupture. There is some other dominant physics that is going on. Okay. But if you've got the correct estimate for rupture, then what you will find is that when you do the analysis and when you do the rupture, you actually will get a rupture time which is of order 1. Order 1 with respect to that non-dimensional time. You understand? So just to mention this, I can show you a result actually for this, precisely for this. So if you see this particular result, there is a rupture that's happening. This would be the nonlinear state of the same. I mean, it's a similar problem, not the same problem. But you can see here that initially it's a flat interface and the film is evolving and rupturing. Now, the time that is being shown here is that the system is evolving in a certain time. And note that these are times are in 0, 3, 6, 9. These are on non-dimensional units. Okay. So rupture is occurring for the system at around a non-dimensional time of 13.22, which means that your estimate of rupture our estimate of characteristic time is correct. If our estimate of rupture time was completely, I've used some other estimate, it is possible that when I do the simulation, and when we compute this, when I ask at what time, non-dimensional time does it rupture, then this number instead of being 13.22, it could be 10 power minus 5 times. The numbers could be really, really small, or it could be 1 million. I mean, it could be very small or very large because you have not got the right non-dimensional number. The very fact that we are getting these numbers, which are order one numbers, tells you that your non-dimensional estimate for the rupture for the time scale is correct. Characteristic time scale is correct. Okay. And looking at the going back to the problem of convection in SL, if you say that my characteristic scale is basically the large overturning scale, but you may be completely off with respect to the estimates of the smaller scales in the problem, the smaller eddies in the problem. Because at the smaller eddies in the problem, some other physics is going on. Okay.
This is actually mind-boggling, sir. It is actually this has cleared so many points. It is, I mean, it is very thought-provoking at this moment, because yes, that is like we are seeing at different scales, so we are seeing at different physics, and we are seeing at then different time scales also. So uh, that is amazing, sir. That this is I got it. I yeah.
Because there's a beautiful underlying, there's a lot of beauty underlying this math. It's just have to one has to it's of course difficult to give this flavor in a course, but I'm happy that you've basically been able to participate in these discussions, which helps me elaborate on this, and I hope eventually some students will look at this, look at the videos, and maybe get some understanding. You the check for all these things is to just see what kind of time scales. The system will also tell you what are the time scales when you actually solve for it. If you do another thing, you can also do it this way. I mean, it's very common for people who do direct numerical simulation. You can just say, I'm going to do direct numerical simulation in dimensional terms. I'm not going to do the non-dimensional terms. I'm going to do it in dimensional terms. Got it? Now, maybe one reason why may want to do it in dimensional terms is because there has been an experiment that has been done, and you are trying to match that experiment. So you know the speed at which people have run a particular simulation or an experiment. You know the current velocity that they have used to drive the flow. It could be flow in a pipe. Okay, you basically set up the same kind of simulation on a computer. Now, when you do the analysis and you start looking at various things that emerge, and you're looking at various times that emerge, let's say you're looking at some time series analysis. The time series analysis could be you have a flow in a turbulent flow in a pipe, and you're putting a probe at a point in space and asking how is the pressure changing. And you'll see that the pressure is, if it's a highly turbulent flow, the pressure will rapidly fluctuate. Now you are interested in what is that time scale. That time scale obviously is going to be much, much smaller than your typical diameter over divided by u. Diameter is a pipe diameter, and then u is the characteristic velocity. Because d by u is like the macroscopic sum, large gross time scale, and that would be the same whether the flow is laminar or turbulent. Sorry, that would be the same thing in a laminar flow as well. But in a turbulent flow, you have newer time scales that emerge. You have fluctuations, and if you want to estimate the time, let's say the d by u is, let's say, 1 second, but the fluctuation may be in 1 millisecond, and you want to get that 1 millisecond. Right? You ask what is causing that 1 millisecond. Where is this 1 millisecond emerging from? Correct. So for that, then you have to ask yourself: is there other timescales present in the problem. And the idea is that there may be timescales in the problem which will point you in the direction of this 1 millisecond, that fluctuation timescale. Of course, it's not that the timescale here we are talking about is a characteristic time. It is not that will straight away tell you the exact value of 1 millisecond. What it will tell you is, if you were to plot the time series, which will be a highly fluctuating time series, okay, and you'll see that if it's over 1 second, you get a million jumps, up and down jumps. Okay, that's why it is around 1 millisecond. But then now, if you basically non-dimensionalize it correctly with a different time scale, which is causing that time scale could be specific to that particular problem, then you'll see that the time scale, the x-axis, over a period of one non-dimensional time, you'll see one fluctuation on an average. It could that's why I said it's an order one number. It could be 1, it could be 0.1, it could be 10. It doesn't matter. But it's not going to be significantly off from the characteristic time scale. So that is another way to. This is another way to choose the. If you here you are doing the other way. You have first done the analysis, getting the fluctuations, or getting the time. The results are telling you that there are several timescales in the system. You estimate these timescales typically from some kind of, let's say, fast Fourier transform or something like that, and then get the timescales. And you ask yourself, are there other timescales in the system that are present? Meaning you do a post hoc analysis, and that will tell you something that is going on about the physics of the problem. Does that make sense to you?
Absolutely, sir. Absolutely, sir. It made it makes a lot of sense. I mean, there's a very deep connection between these things. But sir, sir, I'll go through this paper of yours and try to derive the time scale for my case on my own, and then definitely share this.
If you're using a thin film problem, this paper. If you're using a thin film problem, this paper is important. But if there are other problems, I'll refer to you later. If I know the specific problem, but I think that's good to take it up outside the discussion. You can talk me tell me what is the thing, and maybe if I know some relevant paper, I could direct you in that direction.
I'm actually looking at, sir, bubble rise. So that is there.
Okay. So if it's a, I don't have specifically. We have tried to do some work on bubble rising, but I have some. We've done some work on droplet impact a few years ago. There are several non-dimensional numbers. Let me see if I can share that screen. Yeah, there are several non-dimensional numbers. So this is a droplet that is bouncing on a surface. It basically hits the surface. So it would be something like you have a droplet which hits the surface and bounces back. Okay. So there are several non-dimensional numbers that one can write, and these are not unique. There are other ones as well. So we have Weber number, Reynolds number, Stokes number, or you have a capillary number. Again, capillary number based on the gas viscosity or the liquid drop viscosity. Onshot number. You have viscosity ratio, density ratio. You see, there are several choices for writing non-dimensional numbers. The first step, of course, is to ask yourself how many non-dimensional numbers are there in the problem. So here we say the problem is defined by a set of 8 dimensional parameters. 8. So hence 5 non-dimensional parameters. Oh, sorry, there are 4 independent non-dimensional parameters in this particular problem. Because of the 8, one is our angle. So then we basically ask ourselves what are the various estimates for the problem, and just to get an idea, I'll see if there is a yes. So here, see here, if you look at the result, when the droplet basically comes close to the surface, then I'm getting the thickness of the gas film below the droplet is like quarter 10 power minus 3, which clearly is telling me that the characteristic length scale for the gas film is actually not the radius of the droplet, because it is much, much smaller. But it is actually telling me that the gas film is very, very thin. And there must be another set of physics that is going on, which is actually that's what we use later on. Okay. So, and now again, you see here, there is a time scale in the problem, but if you non-dimensionalize the time scale correctly, this is again going back to what I was saying. There is a time scale, and I can basically come up with a time scale, which is, if I know the radius of a droplet, I think I've done this somewhere, we mentioned this here. Just show this. Yeah, so the time scale would be mentioned somewhere over here. Okay, so I guess this is just the radius of the droplet is given, velocity of the droplet is given, from which you can come up with a time scale. If you choose that as a time scale, which is just nothing but h by v naught or r by v naught, it's not going to work. Okay, so what we do is we choose a different time scale from this problem, and I mentioned. Let me see if I can mention it. Where is that?
Sir, that thin film below that surface, which is the gas film, when the droplet is falling, is that is that similar to the lubrication problem that we have looked?
Yes, absolutely. It is the lubrication problem. So eventually, that there is a lubrication which prevents the droplet from complete with ever making contact. Okay, so I think we have shown this somewhere here. The droplet basically comes and spreads on the surface. In this particular case, I think it is making contact, but it need not make contact. Okay, there is another time. So you see here, here I've written T naught. There I've written you see the time that's varying. This is another non-dimensional time that I've chosen, where the non-dimensional time is h naught by v naught. And you see the numbers, they're like 0.005, 0.001, 0.01. But over here, you see that the time is different. The time over here is order 1. You see it's 1.52. That is because we've chosen a different time here, tau. Okay, tau is basically like a time scale which emerges by balancing inertia to surface tension, because that's the oscillation time scale of the droplet. Okay. So you can look at you can get, this is just a time, this is like a time series. Let's say the contact point, how is it moving, but it's some fluctuation you're getting. But your question is, can you non-dimensionalize it correctly? So can you non-dimensionalize the axis correctly such that you get things of order 1? If you got that, then you've got some estimate of the right physics. Got it?
Yes, sir. Got it, sir.
That's the idea. So you can basically, it says that even though the droplet is, the gas thin film is very, very small, the scale of the contact line position, which are marked as dots in this figure, the contact points here, these contact points are basically comparable to the radius of the droplet, the position of these contact lines. That's why you see that the numbers are like 0.2, 0.5, 0.7. Like close to order 1. They're order 1 rather. Okay. So yeah, I hope that gave you some idea about how knowing the right time scales and length scales in the problem can help you understand, get you some deeper insight into the problem.
It actually does, sir. It actually does.
It is not just for saying that I want some non-dimensional numbers. You should ask yourself, why do I even care about non-dimensional numbers? Of course, one primary purpose of using non-dimensional numbers is because you want to reduce the dimensionality of the problem. If you have 8 non-dimensional numbers, and let's say there are 5 dimensionless number, you automatically reduce the dimension space, parameter space from 8 dimensions to 5 dimensions. But there is also, you get some deeper insight into the relevant forces, force balance, and what is driving physics. Okay. So, all right, if there are no more questions, then we'll call it a day. And thanks for your very insightful questions and this interesting discussion. You can revisit some of these lectures, especially the rupture problem. Hopefully, you get more clarity again.
Yes, sir. Sir, just before we end, sir, there is one thing very important that you referred us to that you said that Rayleigh revisited this problem which was studied by Plato. So I read that paper sections of Royal Society. So there was and when I read that, and in the first line he mentions, I mean in the first paragraph itself Rayleigh mentions that we are looking at this problem because we are interested in something of acoustics, related to acoustics, and he was looking at this problem with the eye of an with the eye where he was thinking about acoustics and taking the Plato instability and trying to explain it with the help of acoustics. So it was very I mean it was very mind-boggling because we are looking at, he was looking at a physics which was he was looking at a problem in physics which could be explained by acoustics. So it's like two unrelated things, but he managed to capture this.
Well, to be honest, these are not unrelated. That's the point that you have to understand, because we have thought of many times one is taught to think of these completely different set of things are not connected. But the beauty in this is they're all intrinsically connected in some way or the other. You may attack one problem. I mean, when Kelvin did his work on vortices, he was doing it to come up with a new theory for matter. He called it the vortex theory of atoms. This was before, because this was when spectroscopic results were available, and people had identified that, when you pass light through matter, there is a spectrum that emerges from this, meaning certain frequencies are absorbed, and they wanted to explain how do you even explain this. So there is light. You can think of light as a wave, and there is a wave is some kind of, there is you want to say how is it interacting with another wave, because maybe there is some constructive interference, destructive interference going on. So you want to explain matter in terms of some underlying waves. Okay, so he was thinking of that. Rayleigh thought about his when he was thinking about hydraulic jumps, he was looking at it as shock waves. Kelvin waves that you see for when a ship moves on the surface of water, you see this beautiful V-shaped pattern. That's an oblique shock. Okay, and but instead of referring to a Mach number, which is the speed of sound, speed of the fluid to the speed of sound, you can generalize this Mach number. You can say, what is Mach number ultimately? It is the speed at which the fluid is traveling divided by the speed at which information can travel in the fluid. If I'm speaking, information is traveling in the air with the speed of sound. But on the surface of water, information is traveling in the form of ripples on the surface of water. So if you use that as a non-dimensional number, meaning the speed of the ripple, the surface gravity wave, then you get a number which is very similar, analogous to the Mach number. But instead of calling it Mach number, we call it the Froude number. Okay. And if you travel faster than the ripple, meaning when a boat is moving, the boat is traveling faster than the speed at which the ripples can carry the information about the boat ahead of it. Therefore, you will get a shock wave behind. Okay. If I remember correctly, and I'm not 100% sure about the history here, Stokes, when he did his first work on Stokes equations, and he derived he looked at the lower and Reynolds number flows. If I remember correctly, I think he had the idea of how ether is moving. Ether is a very low density medium. How ether is moving around the surface of Earth. And because it is such a low density medium, the Reynolds number for that medium is very, very low. Therefore, inertia drops off. It was not with, if I know correctly, it was not with regards to tiny tiny particles that are moving in a viscous fluid. Okay, but I haven't, the last part about strokes, I haven't checked this in a long time, but I've seen this somewhere. But you know, these are all, we tend to think of them as completely unrelated different problems. But then the very fact that a lot of these problems in fluid mechanics are governed by the same master equation, which is Navier-Stokes equations, with some additional physics thrown in, tells you that there is a deeper connection between many of these problems.
So this is, I mean, how do we even start reading that amount of? I mean, how did you come across this thing? How did it started?
So you just have to have an interest in the history of why this somebody did this. You know, you go back to the original papers, you'll find that the motivation for studying them can be very different, which is exactly what you have done. You basically, in fact, a lot of Rayleigh's work, including things like Kelvin-Helmholtz instability that we discussed, Rayleigh-Plateau instability, Rayleigh-Taylor instability, Kelvin-Helmholtz instability, you'll find that they are basically, that's what we did, right? We did a generalized version of it. Rayleigh-Taylor and Kelvin-Helmholtz, two fluids with different velocities, different densities and surface tension. Now, from which a variety of problems emerge. If there's no velocity, then the Rayleigh plateau emerges. By the way, this is something that may not have done it yet. It is there in a subsequent week. I think week number 11, I think it's discussed. Then we also have done only Kelvin-Helmholtz instability. No, I mean without worrying about difference in densities. Purely a shear-driven instability. Purely a density-driven instability, density stratification-driven instability. You can come up with this. A lot of this is discussed in Rayleigh's seminal books, 2 volumes, Theory of Sound, volume 1 and 2.
It's a theory of
theory of sound. Rayleigh's theory of sound. It is worth having a copy of this book.
It's a theory of sound.
Theory of sound. In theory of sound, you will find the Kelvin-Helmholtz, Rayleigh-Plateau, all these instabilities. It is not. Don't think of it as an acoustics book which has no connection to classical fluid mechanics. That is not how a lot of these people did not even think like that.
Sir, it is actually, even if I come across such a book in library, I would.
It should be there. It should be there. It should be there, and you should be able to find it in the Tata book first. I can tell you that. In ISC.
Yes, sir. Tata, I'll go actually in the library to find it then.
Yes. Well, so yeah, okay. So I think we'll call it a day. Thanks for the insightful discussion, Mr. Manshu. Can I request the NPTEL team to stop the live streaming? All right. Thank you very much. Bye.
Thank you, sir. Thank you.